Hi guys, can I get a sound check?
Hello? Yeah, you could.
Great, thanks guys. Oops. Did anybody catch the landing today? Mars landing? No?
Oh,
I didn't. I remember I was actually working at JPL when when was it? This was 94. I forget which one it was, which Mars landing. I was like working in the basement and my brother calls me and he's like, man, that's so exciting what you guys are doing, blah, blah, blah. And I'm like, well, what are you talking about? And he's like, oh, like the landing on Mars from like JPL did all this stuff. And I'm like, what? And anyway, I just went upstairs and the cafeteria is right across from our building and everybody's cheering there and just totally oblivious. It was pretty exciting stuff. But not for us, I guess. Okay, so guys, I'm gonna do, before we do anything, let's just see if we can answer any questions we have about Project1. And so I don't know if you guys saw it, but I changed the due date to be Saturday morning. I guess if you guys need more time, I don't know if there's like any night owls out there or whatever. So that was that. And then I think some of you had some last questions. I think Wencheng specifically, I don't know if he's here. Let me see if Wencheng is.
Oh, here.
Okay, hey Wencheng. So can you, you said you wanted to talk about your question in the class today. And I was trying to figure out like your question, was your question how you would do a transient simulation?
So my question is for part two. You say we need to say out the the delay let me see it's say to say out the delay simulation and then the 2B is say to create the transient simulation.
Yeah.
So we just create a transient simulation. So that's it.
So you're wondering how to create a transient simulation? Is that your question?
不是 you say out your delay simulation and then create a transient simulation. So
Yeah.
the main point is just to create a transient simulation. So that's it.
Well, I think you have to set up. Let me see if I can pop a screen. I have. There we go. Let me see. How do I do this? Just let me see if I can share my screen with you guys. So, wait, that didn't do anything. Let's see. I want to view options. I don't want that. I want to share my screen, share. And we got, what do we got? Here it is. Okay, so do you guys see sort of like it's basically the transient sort of example file I sent. Okay, everybody see that?
Yeah.
Okay, so what you want to do in the delay model, okay, so you'd want to do a fan out of 4 delay. Okay, so what you do, I'm going to see if I can do this. I'll probably fail miserably. So I want to put 4 of these guys down. Boy, that didn't work. Sorry, guys. Get myself situated here. So I just sorry, still simulating. Not the most user-friendly. No. The heck do you zoom in and out? Just remember how to zoom out? I never know. Go. Zoom out. I don't know how to zoom out.
I think you just
What's that?
the scroll wheel.
Do you have a scroll wheel, Professor, like a mouse?
Oh yeah, thanks. Perfect. Thanks,
Yeah,
guys.
there you go.
Thank you. Okay, so these are all loading down this circuit. Okay, so this circuit is going to drive all of these. So I got to draw a draft wire. I've got to draw wires from here to. Can I do this without causing a lot of grief? Oops, what am I doing? Okay, so now I have this inverter is driving another 4 inverters like itself. And this is called a fan out of 4 delay because it's, you know, indicative of how well this might do in reality. It's just an example of, you know, one way to look at delay. Okay, so I have this, and I have a voltage source here. How do I? Okay, so this is the input voltage source to my first inverter. The supply voltage is 1.8, so I'm just giving it from 0 to 1.8 volts. Wencheng, are you familiar with this pulse format as a voltage source?
No, not really. But
Okay, so anyway, it's sort of a SPICE thing, but anyway, this is the interface. So if you just took the file that I handed off, you put a pulse voltage source, or you look up a pulse voltage source in whatever SPICE you're using. And it always has these parameters, which is the initial value, in this case it's 0, the value where the high value for the pulse is, which in this case is 1.8 volts. When the pulse train starts, so this starts a nanosecond after your simulation happens. There's a rise time, a nanosecond, fall time, a nanosecond. It's on for 10 nanoseconds, and the period is 21 nanosecond, and the cycle is 3 nanoseconds. Okay, so I want to simulate, and then, whoops, let me delete this, and then put in this guy. But you guys can't see that, can you? Okay, let's see. I'm gonna try to, what? Great. Hold on, guys. What the heck? Give me a second, guys. Sorry. Are you guys still there? You guys are there, right?
Yeah.
Yeah, we're here.
Yeah, we can see it.
Trying to figure out, I'm trying to show you guys my waveform window, but it is absolutely failing. LT spice, zoom, okay, zoom, window. I have absolutely no idea what just happened. So you guys still see my schematics? Sorry guys, Wencheng, sorry, I can't show you my waveform window, but if you saw a waveform, again, it'd be like, it'll go from 0 to 1.8 volts after 1 nanosecond, and it'll have a rise time of a nanosecond, fall time 1 nanosecond, on of 10 nanoseconds in a period of 21 nanoseconds. Okay, I mean for this particular guy, but just look up pulse voltage source. Okay, and if you're using LT Spice, you can just kind of use what I have here in the transient thing. Are you with me so far, Wencheng?
oh yeah, yeah.
Okay, and then the second thing you need for a transient simulation is the thing that actually the dot statement that tells it what to do. So you got to do a dot trans statement. So this tells Spice do a transient simulation. In this case, I just say 100 nanoseconds. If I say this, it'll just simulate until it reaches 100 nanoseconds, and it'll decide what step sizes to use. Or you could set the maximum step size by doing, say, if I wanted to say the maximum step size should be 1 nanosecond, I would do dot tran 100 nanoseconds and then space 1n for 1 nanosecond. And so if you do that, then basically what you want to do is what you end up doing, assuming it simulates, then you basically plot this node, the input node versus the output node, or not versus, sorry, both. So it's respect to time. So you'll see a pulse train here if everything works. You'll see a voltage, high, low going pulse that will be inverted with respect to this input voltage pulse. And probably given the nature of the circuit, it'll be a lot smaller. Maybe like a volt swing sort of centered around 0, maybe, depending on your circuit. And then you'll basically, from there, you can calculate your delays, rise time, fall time, etc. Does that help?
就是 compare the input and output， 就是 and then calculate the.
Yeah, I wish I could show you the pulse. So basically you plot this node, which is the input, if you guys see my cursor, and you plot this node, which is the output, and it'll look like 2 pulse trains. And basically you want to look at the delay between the input. For the propagation delays, you want to look at the input to output delays, and for the rise fall delays, you just look at the output.
So that means so this is just the delay simulation, just to compare the input and the output, and just calculate the time. Or
Calculate the what, sorry?
I mean 就是不是 the part 2 say the delay simulation, and so what it means is just to compare the input and output for the time delay.
Yeah.
Is that what you mean?
Exactly. Yeah.
Oh, okay.
So you gotta like look back on our slide deck too. And so what we said are important parameters for a logic family are, robustness, which is the noise margins. So that was problem 1, is the noise margin. See how much you can reject noise, let's say. The second thing that's important, we said, was operating speed, which is this problem 2, which is delay, speed, they're all related. How fast you can go has to do with how much delay you have across your logic gates. Okay. And then the third thing we said was important was power consumption. So that's problem 3 of seeing what power consumption is.
Oh, okay.
Okay.
Yeah, okay.
Okay.
Professor, can you elaborate more on number 3, part C?
Numbers 3, part C. Let me pull it up. What am I doing? What the heck is? I don't know what happened to my window. What is this? Oh, here we go. New share. Let's see. Give me 1 second, guys. Let me get my. Where are we? Oh, we go. You guys see the Project1 part 3?
I know.
You see it? The shape?
We don't.
Oh, you don't see it?
You can see the schematics, but that's it.
Oh. Here. How about now?
See your desktop.
Let me try something else. Hold on.
So part 2, we don't have to also graph the output of one of the driven inverters, right?
You do not, no. Let's see, what am I doing here? Give me 1 second, guys. Let me get my neck straight. Wow. What the heck? This has got to be user. This is like nothing's working here. Give me 1 second, guys. I'm trying to get to the right directory and share it. Oh, spring. Okay. All right. Now, share content screen. Now, do you guys see Project1?
No.
Still the desktop.
Hmm. Hmm. Yes. Oh, I didn't say yes. What am I doing?
Yeah, we can see it now.
Come on. Okay. Project1?
Yeah.
Okay. Sorry, guys. Well, sorry, guys. Okay. So this part 2 delay, let me just do, if I'm gonna be like screwing up here, but so if I was gonna just draw it as a schematic, right? So this in like one level of hierarchy up looks like an inverter. Okay, so this part 2 is saying take one of these inverters and drive 4 inverters just like itself. Okay, and then figure out what the delay is across this inverter. And, you know, delay has got several components. It's got, you know, if I was going to draw it, boy, I don't have enough room to draw here, but if I was going to draw it like this, let's say this is my input. So let's call this in. And let's say green is my output. So remember that this is an inverter, and because it's, you know, it's this sort of cheesy circuit, it's going to do kind of something like this. I mean, I'm pretty much exaggerating here, but so the output, which is here, okay, is an inverted version, but because it's a NMOS load, you lose some signal here and here. Okay, so we have some delay parameters here. They are called, this is from this 50% point to this 50% point is called T propagation delay falling, I guess. What is it called? Yeah, falling. This from this 50% point to this 50% point calls T propagation delay rising. From this, from the 90% point to 10% point of this green guy, okay, that is called fall time. And the 10% to 90% of the green guy when rising is called the rise time. Okay, and so altogether, these 4 parameters at the logic design level determine the delay through this circuit, because they're all important. Both propagation delay, which means how long it takes for the input from, basically, you know, looking at from input to output, what is the delay and how long does it take the output to transition from high and low? Those are the 4 important parameters to define delay at the logic level. Okay. And we're loading it down with these 4, which is sort of like a question that came up several times. Like, why are we, you know, annoying ourselves by, doing this is because without a load, this guy would, could do anything, and it wouldn't really tell you what really might happen in a real situation. That's the only thing you're really interested in, is what might happen in a real situation. Okay, so anyway, you don't need to plot anything here. You're just doing, looking at across this guy. Okay. Okay, so sorry, the first question was about part C. Is that right? Can you repeat the question? I forgot who asked the question.
Yeah, if you can elaborate more on part C.
So all of this, this is I'm being really annoying with this project, because I'm forcing you guys to deal with this POS inverter to to show to you guys how much. I think it'll help you guys understand the CMOS inverter much better. Okay, so let me just say that's what we're like doing like this. We see the noise margins aren't so great. Delay is funky. You guys should be seeing like very different delays between rising and falling. All that stuff's bad. Okay. And then the last thing is the power consumption is going to be relatively high. Okay. So what I'm saying is, let's imagine if CMOS didn't exist. Okay. And all you had was this type of NMOS logic family, which CMOS, the big advantage of CMOS is, higher noise margins, and also it's low power. Okay, it's just like 1 over everything. So the question is, let's say you had a chip like you have in your, say, desktop. Okay, and I said, okay, what if that chip, which is, let's say it's a, let me put another color. This is like a theoretical, but it's not too far off. Let's say that chip is a certain size. Let's say 10 millimeter by 10 millimeter, whatever it is, right? So a typical chip that you might have in a desktop. And, we said that economically, there's a maximum power you can remove per centimeter squared or whatever before it gets way too expensive or like impossible to remove that. And I said, in the case of this chip, let's call that 40 watts total power consumption that you can remove from this chip. That, and then you can still use it in your laptop with just a fan or something. Okay, so that's the idea behind this maximum power consumption. Okay, so now this chip is going to be full, and I said, okay, so let's assume that every logic gate, so the inverter you can use as a stand-in for any logic gate, but this chip will have a lot of different types of logic gates, NANDs, NORs, whatever. But let's say for the sake of discussion, we could just use the inverter as a stand-in for the average current. Okay, so because it's a logic chip, you have to make an assumption about how many gates have a 0 on their input, how many gates have a 1 on their input. Because if you guys have noticed, there's a big difference between power consumption in this gate between when there's a 0 on the input or when there's a 1 on the input. So I just said it's 50% low, 50% high, okay, on the input voltages. Okay, so when the input's low, I think the power consumption should be 0. When the input's high, you'll get some, probably, I don't know, depends on what you guys design, but might be tens of microwatts, 100 microwatts. I don't know what numbers you guys are getting. Okay, so then the question is, if those were the parameters, so you had, let's for the sake of discussion say you had 100 microwatt per gate, then the question is, how many gates could you fit into this chip? Okay, so we said half the gates are working. So if half the gates are on, or at 1 input, then you could assume, you got 50 microwatts on average per gate, because the other half are just off. So you just divide 40 watts by 50 microwatts, and it tells you how many gates you could, from a power consumption standpoint, you can afford to have in this chip. Okay, And I don't know what number you guys came up with. Anybody come up with any numbers they want to throw out? No? Anybody come up with any numbers? No? You guys haven't gotten to this far yet? Let me do a quick calculation if these are the numbers. Are you guys seeing, what kind of numbers are you seeing with power per gate? Nobody's jumping in? You guys want to play hardball? Let's see. Khaled? Khaled, are you there? No?
I'll be honest, Professor, I haven't started on this yet.
Oh, you haven't
I'm
started?
planning on starting tonight.
Better hurry up, man.
Yeah, I'm actually on my way back from work right now. So
Okay.
yeah.
All right. Good luck. Logan, did you start?
No, I'm starting tonight.
Okay. You guys are going for it. Okay. So
Yeah.
assuming these numbers, okay, I get 800,000 gates is how many I can have on this chip. Okay. And this was, to demonstrate to you guys the difference between CMOS and all the crappy stuff that came before. Imagine, like we said, the chip in your PC might have 1 to 10 billion gates, maybe more in it. Okay, for the same power consumption. Okay, so this is like not even 1 million gates, but if it was 1 million gates, it would be like 1,000 times less functionality. The one we look at it, 1,000 times less functionality than the chip you have in your computer now. Anyway, that was the intent of that. Does that help?
Yes.
Okay. Cool.
And then for the power consumption, that's what we're gonna find on for the letter B, right?
Yeah.
So whatever we found power consumption on the B, that's what we're gonna use.
Yeah.
For okay.
Yeah. So that's why I said keep this guy. And what you want to basically do is, some of you guys are more clever than me, but I use the different supply here than here, a different voltage source. So I just look at the current getting pulled out of this and multiply it by the supply voltage. But I think LT Spice has like sort of different things you can plot when you get to the waveform window, and I'm sure PSpice does too. And I might be able to do average power or actually plot the power directly. So you would do that across one cycle. So you want to basically, one cycle would be like this. So from falling edge to falling edge or rising edge to rising edge, you want to average the power across both a high pulse and a low pulse. Anything else? Nope.
Professor, I had a quick question.
Yeah.
By any chance, have you ever automated LT Spice?
Have I automated it?
Yeah, like I was just curious because I've been doing it manually and it takes a while.
Yeah.
But then I did see online that like you can script it somehow. I was just curious if you had any experience.
I do not. When I really want to use Spice, I use like the Cadence, not the PSpice tools, but like the Cadence, the real tools from Cadence. And yeah, we've got lots of scripts that do sweeps. We got stuff that does Monte Carlo statistical simulations, lots of stuff. Yeah, you really have to automate But you know, LT Spice, I just been using it for the class because we needed something from, you know, being remote. So I have not, but I'm sure there's got to be ways to do it, but I have not done it. And it's certainly a very good idea.
Okay, I was just curious. Thank you.
Yeah, yeah. Sorry, we're all kind of stuck with it.
Professor, for the power consumption,
Yeah.
just to verify, so you said to multiply the voltage source with the current, or do we have to find the average?
You would, so this is the three, if you guys remember, so what, so let's say if we just had this guy and this guy. So let's say this guy is you know, 1.8 volts. Okay, so there's the instantaneous power, which is the instantaneous current times the VDD here. So that's, in this case, it's 1.8 volts. Okay, if I plot that, depending on your gate, you know, with this guy doing 0, 1, 0, 1, it'll do something like, I might do something like this. So, and this will be when the, this is when Vn is equal to 1, and this is where Vn is equal to 0, or Vn is equal to 1.8 volt, say, okay? And this current might be, I don't know, maybe 20 microamps, 100 microamps, whatever you guys, however way you guys designed it. But this is the instantaneous current, okay? So to get, what you really need is the average current, which is the integral, so P average is 1 over the period. So this is the period, includes a 0 and a 1, okay? So 1 over that. And then you want to integrate, what is it? Would be from 0 to t, the I of t times 1.8 volt dt. So you need, long story short, you need the average power across one cycle of 0 and one cycle of 1.
Got it. And for the function of I and so for I of t, how would you go about finding that function so you can integrate that?
Yeah, so what I do, I'm like, you know, I can't be bothered to do too much automated work. I guess I'm the opposite. I just do everything the hard way. I put a probe on this thing, which you can do a current probe, or if you do a simulation in LT Splice, it kind of almost looks like a fly or something shows up if you put your cursor on the schematic. If you click on it, you'll see the current that's going through this guy. And that gives you, if you plot that, you get this sort of a plot.
Oh, I see.
So you want to basically plot the current going through this, or if you want to plot the current going through this drain, or. Got
it. Okay, thank you.
Sure.
And then IT is the peak of that, or professor, or?
IT is the this is the instantaneous value of that. So depending on, so this guy, you know, I drew it a little nicely, you know, I might do this, I might have a little peak here or whatever. Right. But, you know, so the peak could be the highest value of the instantaneous current. It's important for some other things, but not for average power, because usually the peak is also a very short amount of time. So, you know, I wouldn't worry too much about the peak. I would just sort of try to integrate across this whole thing. And by integrate, you know, if you got something that even looks like a square wave, okay, I would just like read this value multiplied by the amount of time here, read this value multiplied by the amount of time there, and you're good to go. Like you don't need to like plot this in Excel or, you know, do an actual integral or something. Just, you know, plot. What I would do is either, again, somebody mentioned that this LT Spice or maybe P Spice outputs average power, or just, you know, plot out the instantaneous power. If you want to eyeball, it should be a pretty flat. If you guys don't see a flat value here or relatively flat, it's probably something's off. So it should be getting stabilized, and you can just read that multiplied by the amount of time that, you know, this that is on, and multiply the off also by amount of time, and average those.
Got it.
Looks like Ahiezer. Am I selling your name, Ahiezer?
Yeah, it's a Heiser.
Heiser. Thanks, Ahiezer. Sorry. So you had some advice for people if you guys look in the chat on how to calculate, measure that. Cool.
Sounds good. Thank you.
Sure. Anything else? So just email it to me. Unless I don't think I want to do anything with Gradescope tonight. Gradescope has got, my problem with Gradescope is if you put in something that's not, at least what I noticed before is that if you don't have exactly the number of pages as my template, it like blows up. So just email it to me and I'll grade by hand, and I guess I'll email it back to you guys.
Professor, the axis labels, there was a way we could add like text to our simulation profile, or the waveform, but it doesn't look really good. Do you want us to like put it on the PowerPoint and add text boxes or something like that?
Yeah, do what, sorry?
So adding axis labels, right?
Mm-hmm.
There's a way we can add text boxes onto the waveform, the graph itself, in LT Spice.
Yeah.
But we can't exactly zoom out to like make it look nicer.
Yeah.
Is that okay, or?
It's okay. What I normally do when I have presentations, I put in, like in PowerPoint, I just put a text box with the axis titles and stuff to make sure it's easily readable.
Gotcha. Okay.
Yeah. One general rule about presentation, guys. So one of you guys, I forgot, and I probably shouldn't say who, but like you turned in your project already. It looked pretty good. So one thing you want to do in PowerPoints is don't think of PowerPoints as like a document. The same rules don't apply. So if you have a paragraph's worth of information you want to convey, you want to turn those into like bullet points, or, you know, instead of one paragraph saying stuff, you do 1 fact, 2 fact, 3 fact, 4, whatever, 5, whatever. And each one is like a short sentence stating something. If you have a paragraph that's got a bunch of plus and minus, like these are the good things that happen, these are the bad things that happen, you want to put it in like 2 columns where you say, you know, bad, good. And then, you know, if you want to say, well, you know, there was bad and there was good, and there was like notes, like, you know, the notes section would be like, you know, I had a hard time simulating this, or I don't think this is a particularly accurate value for whatever reason. Let's say I want to warn the user that your values or whatever are sketchy. These are all reasonable things to tell people. Okay, and I would make 3 columns. So it's like a very visual. Don't go into, this is just, I mean, like I'm on for the first project, I'm not going to mark you down or whatever, but don't think of this as like the whole PowerPoint business is something you'll use again and again. You use PowerPoint probably like 90% of the time you'll use PowerPoint, 10% of the time you'll use Word, at least in my experience, unless you're in a type of a position where you're writing a lot of actual like user documents and stuff, which is everybody does, but you know, some more than others. But most of the time you are presenting your results in a PowerPoint format. So I'm trying to get you guys used to that. So don't use a lot of bullets. Don't overcrowd your PowerPoints. It's a good time to learn how to use PowerPoint. You know, go on YouTube. There's lots and lots and lots. The whole PowerPoint presentation is like a huge thing about what makes a good PowerPoint, what makes a poor PowerPoint. Check it out now, do yourselves a favor. The reason why there's so much information about how to make PowerPoints shows you guys how important this style of presentation is, which is presentations on PowerPoints, okay? So that was that. And then the second, so this is like going back to Sydney's question about adding access titles or just like letting it go. When I have a conversation like this with you guys, I'm kind of asking you guys to meet me halfway. So there's like give and take, and I'm saying something and I'm expecting you guys to follow me part of the way there. Maybe I'll come over to you guys and try to reach out to you and be, you know, be closer, but it's about a 50-50 conversation, right? Meet me half the way there. You've got to put in as much effort understanding me as I am talking to you. And it's like a typical conversation format that you'd have with friends, etc. When you're giving a PowerPoint presentation, you gotta meet that person, whoever your audience is like 99% of the way there. You are trying to persuade this group of people who are usually decision makers. A lot of times they are at like levels higher than you in the hierarchy, or make decisions about whether you're a good guy or not, or members of your team. They are judging you on the value of your PowerPoint. If they have to struggle to understand at the lowest level, if they're just having a hard time understanding what your slides are saying, like at a very basic level, that's bad. If they don't understand the point you're trying to make, if it's just some neutral presentation of results without saying, are these good results? Are they bad results? Are you suggesting this project be canceled, or you're suggesting another 3 engineers to be added to this project? Are you saying you did a fantastic job, or you need another week? These are all, you got to meet them in your PowerPoint 99% of the way. They do not want to sit there and decipher your PowerPoint presentation. It gets really lopsided. You want to make sure they just look at it and immediately get what you're trying to say, okay? So those are advice about PowerPoint. So pay a lot of attention to PowerPoints, guys. It'll be a big part of your, well, so communication is a big part of your success and failure in your career. You know, like you need to be a good technical person, but if you cannot communicate, you are screwed. So, and PowerPoint these days, for good or bad, is like a big part of the communication. Okay, I'm sorry to harp on that point. Any other questions about Project One? No? Okay. Well, I unfortunately have to cut my office hours short tomorrow, but we still have like about an hour tomorrow morning if you guys need more help, and I'm available with emails. So I think, you know, at least some of you guys are reaching out to me. We're talking and doing stuff, and I'm pretty happy. And I think I'm happy the way this project is forcing you guys to face some of these concepts early on. Okay. All right. So let's now try to, where the heck was I? There we go. Okay, so now I'm going to even waste some more time. This is like a soccer game in the 85th minute. I waste time. So I was intending to talk about the sort of entrepreneurship activities, and I'll still try to spend maybe just 5 minutes before we jump into a very short technical class. Okay, so today I was going to talk to you guys about marketing and selling. And so I think something that happens a lot in my experience is you want to start a company and you're very focused on your technology. You're very focused on like, oh, this is so cool. I can make this thing that does whatever, you know, it has some functionality that's really awesome or whatever. And then you start focusing on, you know, what your logo looks like. All these things are, of course, important. What your logo look like, you know, I should make some business cards, get my website going, blah, blah, blah. But the very first thing that you should focus on is who is going to buy your product, who is going to buy your product, why are they going to buy it, and where are they going to get the money from to buy it. Okay, those are the fundamental questions. Okay, and so, and those people could be different depending on the life cycle of your product. Okay, so like a typical, not a typical successful product has this kind of life cycle. Okay, say number of units sold, say, or number of users. I don't know if you guys have seen anything like this, but it's called the kind of the S curve. Okay, so like if you think about an S curve, this would be like, let's use an example of a cell phone, their cell phone. Okay, so this would be like 1993, where the only people that had cell phones were the extremely geeky, you know, cell phone enthusiasts, or if you were a jet setting executive, you know, this is the days when it was like a brick. You know, again, back in the 90s, before you guys were born, but this is back in those times where like enthusiasts would be the ones buying cell phones. Okay, this would be when, you know, somebody like me starts buying cell phones. I'm not that, I'm enthusiastic about some other things, but cell phones, I guess I was a grad student too, and I couldn't afford cell phones. So it became available. I don't know when I bought my first cell phone, say 94, say, or something like that. This is where everybody in the world, this is where when your grandma buys a cell phone. Okay, so this is how it looks. It's an S curve. You know, that's a successful. Unsuccessful products do, you know, bad stuff like that. Okay, so what does this have to do with the people that buy your product? It's basically the people that buy your products are going to change with time. So early on here is where you have enthusiasts. Okay, they are great. They're the guys who would be, I don't know if you guys have heard about Kickstarter. I hope you have. But they're the guys who would contribute to a Kickstarter program because they just love this stuff. They're the guys who will find you no matter how obscure your website is. They're the guys who'll, you know, just love, or just love something new for whatever reason. They just hear, or for whatever reason, I'll use an example. They want to use your product. Okay, so here is, you know, your average consumer again. So they have seen some benefits. These guys have created some advertising. They've created some history of why this product is good. Then these guys start hearing about it and start buying. And here again is where like everybody's bought it, and basically your product is so cheap that maybe like everybody has it, or just become part of everybody's life, or everybody who is in your market. Okay, now every one of these places has its own issues. Usually in a startup, you're from here, you're going from here to here, okay, or from here to here. Okay, like you're probably in a startup, you're not anywhere here, or else you're like ready to go public, or maybe your market's small, or you're like sort of established person. So usually you're here in a startup. Okay, so there are two distinct categories. People who are really enthusiastic here, doesn't matter what the prices, doesn't matter your marketing, whatever. Even if your product kind of is kind of a little shaky, it doesn't work all the time, isn't very reliable, they'll work with you as long as you are responsive. They're like craving communication with you, etc. So that's this group. And this group, you better have your product straight, okay? So let's use an example. So I'm like part of a investment network down in San Diego. They're specialized in life sciences. So we were talking about, somebody was giving advice to somebody else about this new surgical product that they wanted to launch, okay? And they were suggesting to launch the product first in Europe, okay? It's like a disposable thing that's got a camera and whatever, stapler, etc. And the guy was in fact suggesting that they launch in Germany, because in Germany, a lot of young doctors, I didn't know this till the day before yesterday, a lot of young doctors early on in their career need to have publications. I guess it's part of the German medical system. So basically, these would be these early people who buy your product. In this particular case, they may be enthusiastic or not, but they're buying it to get a publication, and their purpose is to, you know, add something to their resume so they can progress. So you have to know, like, they're great because they're hungry, right? If you go to, apparently, if you go to a German doctor with a new medical product, they're going to be very receptive. They want that thing to write a paper for their resume. They're not going to care if it costs $200 or $2,000. They'll buy it from you because we'll get a paper out of it. By the time you're here, okay, you're going to be going, in this particular case, again, in Europe, you're in a whole different game, okay? Starting here, you're selling it to actual medical practitioners. And in Europe, I guess it's all public single payer system. And it's all about cost. They're trying to reduce cost. It's all the government's paying, et cetera. So here, they absolutely and positively only care about, you know, there's how, of course, you know, what it does, efficacy, I guess, that it works, but also about cost. Okay, so here you have a different, for the same product, you have a different customer base than you have here. Okay, so in every one of these cases, you have to know ahead of time, been really thinking about who is your customer, who's the end customer, how do they make a decision, and like how much they're willing to pay. Okay, and it can even change between points in the market. Anyway, like I see this, successful businesses are focusing a lot on this, and especially, you know, this early part launching, et cetera, on who's going to buy your stuff, not just, you know, look at how cool what I'm making is, which is what engineers typically tend to focus on. Okay, so anyway, that was the entrepreneurial hour for the day, and now we're going to jump into MOS transistors. Okay, so so far we've looked at the like a transistor as if it was just a switch, more or less. So we know we have an NMOS and we have a PMOS. Okay, and all we said was that if this is the gate, this is the source, this is the drain, this is a gate, source, drain. Source and drain are interchangeable. So, you know, symmetric, but I'll tell you guys when you can assume what is a source or a drain. But for the purpose of this, I'm not going to worry about it. So we said in the NMOS, if the gate is a 1, whatever that means, it looks like a closed switch between drain and source. And if the gate is a 0, it looks like an open switch between drain and source. Okay, and the reverse is true in a PMOS. Okay, so that's what we said so far. And then we added saying that, you know, NMOSs are good at passing a 0 value from drain to source. And are bad at passing a 1. Remember that, especially in a CMOS process, is a logic 0 is actually 0 volts, and a logic high is your supply voltage. Okay, so in your, like in our project 1, it was 1.8 volts. It could be, you know, we're going to use 1.8 volt a lot, but it could be 1 volt, it could be 1.8 volts, could be 3.3 volts, whatever it is. But so we're going to use 1.8 volts for a lot of this class. Sometimes we're going to use 1 volt, but anyway, the supply voltage. Okay, and then P MOSFETs are good at passing ones, at passing ones, and bad at passing zeros. Okay, so that's what we said. So now we're gonna get into what is actually it happens. Okay, so far we've been treating them as ideal switches. Now we're going to look at the specifics of how they work. Okay, so so first thing first is that the MOS transistor has, at the very least, has like 2 fundamental things that we worry about from a digital design, circuit design characteristics. Analog, you know, you have a few other characteristics. In a digital circuit, for the most part, we care that a MOS transistor has a current output. Okay, and so like a current capability. So if this was a ground, it can pull down certain current. Okay, so we care about the current. What kind of current? It gets source or sink. And if it was a PMOS, we're typically sourcing current from the supply. Okay, so either way, you care about the current. And then you also care about capacitance. So the gate of a CMOS FET has some capacitance. The drain has some capacitance. Okay, the reason you care about that is because something else is driving your, there's another CMOS gate driving your input. Okay, so what does that mean? Okay, whenever you have, you know, we had a CMOS inverter driving another CMOS inverter. Or let's say it's driving, there's something else is driving this. This is like a NAND gate. Something else is driving that input. Okay, it's always driving capacitive loads. Okay, notice these are gates. These are MOS gates. These are MOS gates. Okay, you're not driving a resistive load. Okay, you're always driving a capacitive load. So you're always sourcing current into a capacitive load, or you're sinking current from a capacitive load. Okay, and what does that look like? So I'll always have to write this down. So charge, when you're putting charge into a capacitor, voltage, you get this kind of equation. And if you want to see current, you take the derivative with respect to time of both sides. So dq dt by definition is current. Okay, so if you want to see dv dt is I over c. what's dV/dt? Okay, when we're talking about rise time. Let's think about the rise time. So we said, okay, like the output has this, we got this 10% to 90% transition that we're looking at in problem 2 of the project. Okay, so what that looks like is you have, if it was a CMOS circuit, what would be happening in that case is, let's say I'm driving another 4 inverters like myself. I'm just going to draw them as sort of a logic devices, but they just look like myself. So this is a FFO4 fan out. So what's happening if I'm looking at this is I'm sourcing current into this node from the supply into this node, pulling this node up. So that's what's going on here. The PMOS is putting current in and increasing the voltage on these capacitors and these gates of these devices. Okay, so that's my dV/dt. So I'm looking at a change in voltage, delta V, as a function of a delta time. So, I don't know, if you want to look at it more discretely, it's kind of like that. Okay, is equal to I over C. Okay, I is how much current this guy is sourcing, and C is how much all these capacitors add up to, all these various capacitances. So the gates all have capacitances, the drains have capacitances, but so what ends up happening is that delay in CMOS logic is all about these two parameters for first order. The current that your gate is sourcing and all the capacitances that your gate is driving. Okay, so those two are the critical factors. So we're going to look at what the current looks like, and then we're going to look at what the capacitance looks like in sort of great detail. Okay, so but those are the two important things. So let's first think about like how a capacitor, a MOS transistor works. I'm sorry. And so the starting point with a MOS transistor is a MOS capacitor. So we're going to start with a MOS capacitor first and add the source and drain to it. But the MOS capacitor, all it has is it has a gate, which is where the polysilicon is. So this is that's the poly. That's the so-called metal, because it used to be metal back in the day. Then you have silicon dioxide layer, which is oxide. And you have the S, which is the semiconductor. So that's MOS, okay, which is the substrate connection. Okay, so a real transistor has, so let's say if it's an NMOS, which is sort of like this is intended to be, also has a drain and a source, like you see in your SPICE simulations. I mean, it has a substrate connection and a gate connection. But right now, because we're looking at a MOS capacitor, we have not put in these two connections yet into this. So we just have the gate and the substrate and this sort of capacitor structure. Okay, everybody with me? Anybody questions? What we're looking at here is just a MOS. It's just the capacitor part of it, and then we're going to add drain and source. Anybody not seen a MOS capacitor or MOS transistor? Have you guys all seen MOS transistors in your earlier classes?
Yeah, I've seen one.
Okay, everybody, okay, good. Everybody's seen one. Okay, so this is, I'll go through it fairly quickly. Of course, you guys know how deep we can go into this, but let's go through it real quick. So what does a NMOS transistor looks like? If we were going to build it, I think we talked about this already. Actually, let me put this over. No. Let me see, what do I want to say? Yeah. So basically we saw, whoops, drawing. So we had, you know, the silicon substrate. We put in the oxide and we put in polysilicon. And then we said for an NMOS, this is a P-type. Okay, furthermore, you know, NMOS, I guess I'll draw it, had the source and the drain thrown in. But let's say it's like P-type to begin with. Okay, so a P-type silicon has what's called acceptors. So it's got a lot of acceptor atoms added into the silicon. So acceptors are typically, it's usually boron. Okay, so if you had if this was pure silicon, pure silicon, silicon atom has 4 valence electrons. So it means that in a lattice, you'd have, you know, 4 silicon atoms sort of sitting each other, all sharing 1 electron. So you'd have, you know, the central guy has 4 valence electrons and sharing it with 4 neighbors. So that's like in a perfectly pure piece of silicon. In a P-type dose silicon, so in a cubic centimeter of silicon, I think there's something like, I don't know what this number is, but it's 10 to the 22 atoms in a centimeter cube. So a typical doping concentration for boron into the silicon might be 1 times 10 to the, I don't know, could be anything. Let's say it's 10 to the 15. Let's make it 16, what the heck, per centimeter cubed. They'll make it easier to do this calculation. So if this is the case, okay, every 1 millionth, so for every million silicon atoms, 1 atom got replaced by a boron atom. So they're still pretty rare. You're really still talking about a chunk of silicon, except 1 part in a million is like these boron atoms that basically they're lacking. They only have 3 valence electrons, so basically they add a hole to this area here. So basically what they do is they make the predominant free carrier in this area, wherever there's a P, the predominant free carrier is a hole. So it's a positively charged particle. Well, it's like a lack of an electron in the lattice, but electrically we think of it as a positively charged particle. It's not really a positively charged particle. It's just a hole is a lack of an electron, lack of a mobile electron that's sort of moving around the lattice. Okay, so that's why this is a long-winded way of saying, sort of reminding you guys why the P-type silicon here in the bottom has a bunch of positive charges. These are the holes that are generated because this is P-type doped. There's a bunch of boron. The reason I keep mentioning boron is as far as P-type dopants goes or acceptors go, it's pretty much all I normally see as boron. Okay, so a bunch of positive mobile charges here, and let's say you now put in a negative voltage on the gate of your capacitor, of your polysilicon, compared to the substrate. Okay, so substrate, gate, you put negative charges here. When there's a bunch of mobile positive charges, what happens? Well, the negative charges on the gate just start attracting positive charges. So basically these things kind of rush to the surface, nothing happens. Okay, you got minus on one side, plus on the other side. It looks like a capacitor. So this looks like a capacitor with the thickness of the gate. So the thickness of the silicon dioxide sets capacitance per unit area. Okay. Now, what happens if I go the other way? What if I start putting positive voltage on this gate? Well, if I put positive here, this area was full of positive free carriers, or free to move around. So positive repels positive. Okay, so if I start putting positive voltage on the gate or positive charges on the gate, they are going to repel these positive carriers away from the gate area, away from under the gate. Okay, so physically you have the gate, you're pushing, physically you're pushing these holes away from the gate. Okay, and when you push the holes away from the gate, you get an area that's depleted of these free carriers. So we call that the depletion region. It's depleted of free carriers. Okay. So if you keep doing that, okay, what happens is, you know, in a piece of silicon, we have majority carriers. So in this case, majority carriers or holes in a p-type silicon. Carriers, holes for p-type. But we also have some minority carriers, which are electrons. So in a p-type doped semiconductor, you have much more holes than you have electrons, maybe by a factor, I mean, it depends on the doping concentration and so on, but it might be by a factor of 1,000, 10,000 different, something like that. But there are some electrons, and eventually you start building up as you increase the voltage past a certain point, you start getting a bunch of those electrons actually get attracted to the surface. Okay, and so they basically you'll end up going from a capacitor that was just as thick as the oxide in this case, to a capacitor that looked like it was thicker than the oxide, because this looks like a parallel plate capacitor, but this separation is more than just the oxide thickness. It includes this depletion area. Back to a capacitor that is just as thick as the oxide. Okay, so you go from high capacitance to lower capacitance to back to your original high capacitance. Okay, and when you end up in this case, once you get past a certain voltage, which we call this is called the, by definition of when this is called the channel. This is an inversion layer. Inversion. The reason it's called inversion is because this area inverted from the original P to N type. Okay, it sort of inverted its status. And when this happens, by definition, this gate voltage is defined as the threshold voltage. Okay, now I'll just say one last thing and just leave it at that. This, this V sub T gets used a lot in in transistors. This is not the same V sub T you might, if you guys are familiar with bipolar transistors, not the same V sub T. This V sub T is again, the threshold voltage of a MOS gate. And they can basically tune it to be a whole range of values, you know, like a V sub T of a bipolar transistor, like at room temperature, is always 25 millivolts. But basically, the threshold voltage of a MOS transistor, it could be 300 millivolts, it could be 800 millivolts, it could be 1.2 volts. They can just basically tune it by the doping concentration here and the thickness of the gate, etc. So I think that's one of the, and it can vary a lot across across manufacturing. You know, like you get wafers one time, their threshold voltage is 400 millivolts. Another time you get another set of wafers, the threshold voltage is 300 millivolts. It can vary. So that's by definition a threshold voltage. Okay, guys, I'm gonna stop here. And then in the next class, we're gonna add the drain and source to this device and get our full NMOS transistor. And then we're gonna start looking at current flow. Any questions?
None so far.
Nope. Okay,
I just
guys.
had a few about the project, but not the lecture.
Okay, did you wanna hang on after? I'm okay to hang on for a few more minutes if you wanna ask now, or?
Yeah.
Okay, go ahead.
So I was plotting the current for part 3. That's supposed to be coming from the source VDD, right?
Yes.
And mine's going between like 0 and the negative current value.
Okay.
Is that correct?
Yeah, it's fine. It's just saying that it's like, depending on where you sort of do your current, where you poke at your current, if you're putting it on the supply voltage or the drain of that device or the source of that device, it'll end up being positive or negative. It's just,
Okay.
it just has to do with your cursor, how you put it.
Yeah,
But
because I just had it measuring from like the source itself, and it's going between like 0 and a negative. So
yeah, what's is it? But does it look kind of like a square wave?
yeah, it's pretty square.
Okay, and then what's the current value?
It's, let me put a cursor. It's negative like 389 microamps.
Okay. Yeah, I mean it's on the high side, but it is what it is. You made a strong driver.
Yeah, just put it on the grain of the inverter. It will turn positive.
So the drain of like M2.
M2, yeah. Or M6.
Yeah, mine's called M6 too.
Just make sure that it's on that first inverter and you're not like hooked up all the supplies to it. Or if you're poking at the drain, you're actually okay.
Yeah. And then I want to kind of space a little bit. So TPDR and TPDF, that's the time between on the output voltage, like 50% up on the rise and 50% on the fall.
So so the prop delays have to do with delays from input to output. Rise and fall time delays have to do with just the output transitioning. So the prop delay rise is like this. So if this is my, say like this is my 1.8, I don't know what you have, but you know, let's say this is 1.8 volts. This is my input. I don't know, whatever, 0 to 1.8. And because you have this NMOS transistor, sorry, MOS load, you're doing something like this probably. I'm gonna guess. I don't know what does it kind of look like that? Does the output?
Yeah, kind of.
This might be 1.4, might be 1.2. I don't know. Depends on how you designed, and this might be 0.2 volts, let's say.
Yeah, I think mine, like the upper side has like a slight curve to it. And like, yeah, so like the max is like 1.2.
Kind of like this. Whoops.
Yeah, a bit.
Yeah.
There's just like a slight angle up.
Yeah. It's sort of like little. It's that MOS is kind of slowly turning off. Okay, so the prop delays are defined as the delay from the input transitioning to the output transitioning. So this would be TP, like falling prop delay. So from the input being at 50%, so while the input is going from 0 to 1.8 volts, and it's at the 50% value to when the output hits its 50% value.
And we just subtract those two, right?
Yep.
To get,
Basically, it's this time.
got it. Okay.
Prop delay falling, yeah. And then prop delay arising is from this 50% to this 50%. So now you got to be a little careful. So this guy's 50% point may be different than, so it might be like, you know, the 50%, they might not be like exactly centered on each other. Again, depends on your design. You see what I'm saying?
Yeah.
So just make sure it's from 50% on the input, 50% on the output, wherever that wants to be. So yeah, 50% could be here, could be here, whatever, but 50% of this green line, and then 50% of the green line, and red to green, red to green. And then the rising and falling has got nothing to do with the input. It's just got to do with this
90% to 10%.
or that
90. Yeah. All right. I think that should be. I've been a little confused trying to figure out the noise margins, because like I was pretty sure I had it, and then I tried to go in and check it, and then I was just confused actually looking at a graph.
Okay. Yeah, noise margins can get really, really confusing.
And then like I check it online, and one person says, "Oh, it's this," and another person says it's like this. And it's like it's not quite the same.
Yeah, my only suggestion is I think they're defined in slide deck 2 or something. So go there and see, just sort of like follow those instructions. Otherwise, just send me what you got. I'll look at it tomorrow morning, and I'll let you'll get a third opinion from me.
All right. Yeah, because I think I was looking through his slide deck and I just couldn't quite.
Couldn't see where it was defined.
Yeah, because like I could kind of see, and I even watched like the lecture of it.
Yeah. Which one was it? Was it this guy? So this is kind of, do you see my screen? So
yeah,
slide 19 is probably like a good, I don't know, can I erase this? Yep. Is probably a good indication. I mean, this is probably the same circuit as what we have, except, it's 1.8 volt, 1.8 volt. Okay.
yeah, because it doesn't really say like why we put the dots for the low and the high, or at least it's not quite clear to me.
Yeah. So let's try to think this through. So let's see if you have a better definition.
So I was like, oh, so maybe it's like when the slope's like the greatest.
Yeah. So basically you want a situation where your slope hits -1. Those are like the definitions of your the V input low, okay, is this is a weird description. Okay, so like I gotta even think about what I'm saying. V input low is the highest low value that still gives you legitimate 0. Okay. So, low values like a 0 value goes all the way from, 0 to this. Okay. This is all a legitimate 0. So VIL is the maximum value that still gives you a legitimate 0.
Okay.
And that's where the slope is -1. The reason for it is if you go beyond that slope, okay, if you go beyond -1, beyond -1 means you get a higher value for your slope. That slope is the gain of your circuit. Here you have a lot of gain. So if you have if you have a little bit of change on your input, you get a big change on your output. So you want to avoid this place. It's not a good place to be for a logic gate, because you want to basically suppress input variations. You want a flat high and a flat low. You don't want to be like amplifying the noise on your input to be on your output. You don't want a higher noise on your output than you have on your input. That's like an amplifier. That's not what you want. So you want to stay below the slope of 1. The -1 is incidental. You want to stay below a slope of 1. If you're a slope greater than 1, means you're gaining up your input at your output. See what I'm saying?
Yeah.
And the fact that it's -1 is just because it's pointed in this direction. Okay, anyway. So, and then the same thing, a VI input high is the lowest value that's a legitimate 1. And that range goes all the way to your supply voltage. And so both of those guys are like defined by the -1 slope. We got to kind of find that.
Yeah, I was trying to figure out how you measure the slope in LT Spice.
Like again, I'm not gonna just go roughly where you think it is and just explain what you did. Like if it's exactly -1. You can kind of see it, right? You can kind of see where it's making that transition from like convex to concave kind of thing. I don't know.
Definitely easier on the input high side.
Yeah. But it depends. I mean, it is a pain in the ass, I guess, with this NMOS thing, because it's not a very, like it's actual CMOS thing. If I plotted the actual CMOS transfer curve, it kind of look like this. So it'd be a lot sharper and more obvious where the transitions are. Here it's like a lot more smooth, so it's kind of hard to see the negatives. But anyway, look at the -1 slopes, and then that'll tell you it'll tell you V input low and V input high.
And so those values are just directly like the
-1 value.
like the Y value at that point.
So now V output low the output low is the lowest voltage that your output sort of produces. Okay. So like basically this is the range of, so this is your sort of V output low.
Okay, so that's like just the minimum.
That's like the minimum you can produce. Yeah.
Okay.
So it's kind of like this low noise margin is like the difference between the, so what it's looking at is you have one inverter driving another one. Okay. This guy defines the output low. That's the lowest they can pump out. That's the lowest they can possibly pump out. And this V input low is the highest this input will still accept as a legitimate zero. And the difference between those is your noise margin for a zero or noise margin for a low. Okay, so you're basically means you would like to have the output low be all the way to ground, but just the reality is your output can't go any lower because of your, your inverter. A CMOS inverter can go all the way to ground, but your inverter that you're designing now cannot. So there's no point saying that's like part of my noise margin. It's not. So you got to, the noise margin is the difference between that and the lowest thing that the gate it's drawing will accept as a zero. That's your margin. So if this guy can vary between those values, and this guy will still see it as a zero.
All right, and then V output high is just basically where it's at 0 volt, and just.
Yeah, V output high is like, this is going to have a maximum of high output, and this will exceed the lowest value where this guy will accept a 1 is the V input high.
All right, and that should definitely clarify a lot.
Yeah, and those are the so remember what we were trying to see is how these noise margins tell you how the bigger your noise margin high and noise margin low is compared to your supply means that you can use a bigger amount of that supply as a legitimate 1 and a legitimate 0, means that if you have a lot of noise on that supply or on your inputs, it'll reject them. So it's a noise margin. It's like a noise rejection capability. And the larger it is, the better.
Okay. I think that's everything I was confused on.
Okay, cool.
Thank you.
Okay, take care, Connor. Any other questions about Project 1?
Guess not.
Hmm?
Thank you.
Nope. Okay. Okay, guys. Have a good night.
Thanks, Professor.
Thanks. Bye.
Good night, Professor.
Good night.